Okay, everybody, let's talk about this sorting. We did this last class, but I'm just going to repeat a little bit to review a little bit. Okay, we have two sorting algorithms, two sorts. One is called selection sort. The other one is insertion sort. And there are many others, but today in this semester, for this class, we will just study those two. Selection sort, basically, it's because of the name, you know what it does. It selects, okay, that's why we call it selection sort. It selects the smallest element and place it in the index 0th position. And then it selects the next smallest and place it in the index 1 position, and then selects the next one and place it at the index 2 position, and so on. That's how it works. So if you look at this once again, okay, this is position 0, 1, 2, 3, 4, right? We have 5 elements, and we scan through the list, see to find the smallest one, and this is the smallest one. And so we place this element here and place this element there. And so now we have this list, right? 1 comes here, 3 comes here. And then we go to the next element, the rest of the list, because this is done. It's in its final place. And so we look at this list, find the smallest one and place it here, switch, swap, place it here. And that results in this one. This is the sorted list. And then we scan the rest of the list, find the smallest one, which is 3, right? So we switch it. We put it here and this one here. And now we have these sorted, right? And then we look at the rest of the list, find the smallest one, which is this one. And we switch it with itself, okay? It's a in-place switch. So you think for human beings, we know immediately that, oh, it's in its own place. We don't need to do anything. And you also think, oh, this list is sorted. Why do we need to sort again? We will stop right there. But for the computer, it's very rigidly follow the algorithm. The algorithm is once you find the smallest one, you need to switch it to the right location. So that's why it will do the switching. And also, even though you think this is listed, it's not. So the computer will contain, oh, I'm sorry, here it actually, this is the last one, right? After this round, this is the last one. So it's sorted. Yeah, for this one, yes. Because once you place this in place, once this is in place, this is the leftover. So it's by default, the last one, the largest one. So that's the sorted list. Okay, so now if you look at this, there are 5 elements. You go through the list 4 rounds, 1 round, 2, 3, 4. Why? Because the last one is sorted, right? It's the leftover. So you don't need to compare it with anyone anymore. It's by default in the right place. So if you have 5 elements, you will go through it 4 rounds. And we call each round a pass because you are passing through each element. So 4 passes. If you have 10 elements, you will need 9 passes for selection sort. And it's because the last element is by default sorted and in its right place. That is selection sort. And I gave you an example here, and you can look at it. And the swapping, we discussed this. This is how you swap. You place one element in a temporary variable so that you don't lose it. And then you change, right? Okay. And we discussed this also, polymorphism in sorting. That is, when we declare a method, we want the method to accept a comparable object instead of an individual typed object, instead of a char, a double, an int, because in that case, you have to overload the method with all the different types. And you can never exhaust those types because programmer-defined types like what we did, book, student, class, course, all those types, you cannot exhaust them. So the best way to solve that problem is to use polymorphism, to have the method accept a comparable object, right? A list. This way, if you want to sort your list of a certain type of object, just make sure that object implements the comparable interface. So this way you define a method once, and then you can use the method to sort any objects that implement the comparable interface. So that we also discussed the Compare2 method, right? I implemented the Compare2 method. It returns an int, and here I already explained it, so I don't have to repeat that. Okay, and we talked about this one, right? Let me just make sure you understand this. This friends is an array of type contact. Okay, so let's look at contact. Contact implements comparable. So now we can actually sort contact, right? Because it implements comparable. And constructor, toString, those you understand equals. This method is from object, you remember. So you compare equals, and for this project, you do not care about phone, whether they have the same phone number. As long as last name and first name are equal, then they're equal. That's how you define equal. And we need to cast this other to contact because we need to get the last name of this object, right? So object does not have the get last name method, only contact has. That's why we need to cast it. And we discussed that also. And this equals is the method in the string class. The string class has overridden the equals method already. So you just simply use it. And now let's look at the Compare2 method. You accept an object, and then because you want to compare first name and last name, you simply get the first name and last name of this other object. You cast it again to call the get first name and get last name method. They are here. And if the last names are the same, then you will compare the first name. Okay, because the string class has implemented the Compare2 method, so you really just call the Compare2 method of the string class, and that will return a positive, negative, or 0. If last names are not equal, then you will compare, oh, I'm sorry. Yes, if last names are not equal, you simply only need to compare the last name, right? So that's how you implemented this Compare2 method. And so now, because we have that, we can call this selection sort method, which is static. It is in the sorting class, and you can download this sorting class from the source code. If you go to modules, you go to the bottom, near the bottom, you should see source code. It's a zip file. You download that, unzip, and you should find in chapter 10, right? You should find that class. So you do not need to write it, you just use it, okay. And you are sorting friends, which is this array, and then you display it, and that's the display there. So this for loop, let me just briefly remind you how this works. This is the data type. This is just a variable name to reference each element, colon, and then this is the array name. Okay, and then you print out each element. Because the variable name is friend, you just print it out. You reference each element using friend. That is the for loop. This type of for loop is for access only, for read only. you cannot use this syntax to change an element. To change an element, you must use the square brackets, the subscript, using an assignment to change. Okay. Now let's look at this selection sort method. Okay. Because you know the algorithm already, the algorithm is to find the smallest element, place it in position 0, and find the smallest, next smallest, place it in position 1, etc. So this is how it's translated into code. And I'm going to just trace this so that you understand the code a little bit better. Okay, so when you trace an algorithm, you will put the variable names there. So I'm giving you this example, this list. That's the list we just discussed. Okay, these are the indices, right? Those are the indices. And these are the actual element. Okay, we have 5 of them. And so first index is 0. So I put index 0 there. And then we do indexes less than list.length minus 1. Why do we do length minus 1 instead of list.length? If you remember, I said the last element is the leftover. By default, it's all the smaller ones are picked. So the last element by default is the largest one. That's why you do not need to go through that. That's why you do list.length minus 1. So that would be 4, right? List.length is 5, and this would be 4. This way, you don't go through this element. Okay. Main is index. So index is 0, main is 0. Okay. And then, okay. So within, this is a for loop, right? And then within this for loop, you have another for loop. This is called a nested for loop. And this is called the outer for loop. This is the inner for loop. Okay, nested for loop. So for this inner loop, we do scan is equal to index plus 1. Index is 0 plus 1 is 1. So that's the value for scan. Okay. And the scan is less than list.length, which is 5, right? So this loop is doing the comparisons if you look at it. So we are doing list sub scan, which is list sub 1, dot compare to list sub min. So what is it? List sub 1 is 9. No, I can, okay. Let me just not do this. Okay, so list sub 1 is 9, right? Close it. I cannot. Keep. Okay. Okay. So I can type that way. It's faster. Okay. Oh, okay. I will just do that. How about I cannot do it, right? Okay. Let me stop recording. Okay, I just deleted those markers, but you remember here it is 4, right? And here it is 5. Those are the only things I have had there. So, okay, list sub scan is 9, right? Because 1, that's the position, and 9 is the element. Dot compare to list sub min is less than 0. That means if we are comparing, if the first element is less than this element, list sub min. And list sub min is what? Min is 0, list sub min is 3. So 9 is less than 3, that's not true. If it's not true, we skip this element, we skip this statement, and we increment scan. So scan now is what? It's 2, right? Scan is 2. And scan is less than 5, that is true. And we come here, if list sub scan, okay, list sub scan 2, and the element is 6. So, so the first one is false, right? And then we do 6 less than list sub min didn't change. Our main index min didn't change. So it's 3, right? The element is 3. And that is false also. 6 is not less than 3. That's false. So we skip this statement and we increment scan. And scan now is 3. And so 3, that's 1. At index 3, the value is 1. 1 is less than, list sub min is 3, right? Still 3. 1 is less than 3, that is true. So this condition is true. Now we change min. That means we found a value that's less than the very first one. We just assume the first one is the smallest value, right? And then we begin the comparison. So now we found 1 and we change min. So min now is scan. And what is scan? Scan is 3. So min now is 3. Okay. And then we increment scan. Scan is 4, right? Scan is 4. And scan is 4. Okay. Scan is less than list dot length is 5 here, right? And so 4 is less than 5. So it's true. And we continue to do this comparison. And that is what? That comparison. Okay, that's 2. The element at that position is 2. List sub scan, list sub 4 is 2. 2 less than list sub min. Now our min has changed. Our min is 3, right? That's the position. So we go to 3. The list sub 3, the element is 1. So 2 is less than 1. That's not true, right? That's false. So we skip this statement and then we increment scan. So scan now is what? It's 5. And you do this. 5 is less than 5. That's not true. We get out of this loop. We go to the next statement, which is this one. So what is temp? Temp is list sub min. We assign list sub min to it. And min is 3. So list sub min is 1, right? That's the element. So temp is 1. And list sub min is equal to, that means 3 right here. That's min, right? So list sub min is equal to list sub index. What is our index? Our index remained 0 because that's the first round. So that means instead of 1, now it should be 3, right? So this is really gone. It's replaced. And then list sub index, that's index is 0, so it's here. Now it's temp. And temp, we remembered it here, 1. So that's the swapping part. So it's 1. After this, we sorted the very first element in position 0. Okay, so you can see what this loop does. This loop is going through the list to find the smallest numbers index. Okay, it goes through the list, find the index for the smallest number, and then swap, place that value in the first position, and then the next one, and then the next one. So that's the function of this loop. Okay, it does the comparisons and find the smallest value. What is the function of this loop? This loop goes through the whole list. It goes through each position. So the first time it goes through position 0, and we just finished it, right? So now 1 is at its final place. It will not change anymore. And then after this statement is done, what do? We increment index. So our index now is 1. I'm not going to go through the next round, but you got the idea. So now our min will be 1. We assume this is the smallest value, and then we begin to do the comparison. So scan now is index plus 1. Scan would be 2, right? It would be 2. And then you compare 9 with you compare 6 with 6 is less than 9. That's not true. So you will swap. You will change the index for min. Okay. Do I do this? Let me see. Do I need to do this, everybody? Let me think. Okay, everybody, I'm going to do the next round just to make sure you understand the algorithm, right? So we finished the first round when index is 0. Now, after we finish this statement, in the first round of the outer loop, we increment index. So our index now is 1 instead of 0. I'm going to delete 0. And then main is equal to index. Main is equal to index right there, right? Okay, so for int scan is equal to index plus 1. So our scan now is 2. And less than 5, that's true. And we do list sub scan, which is list sub 2, which is 6, is less than list sub min. And min is what? Min is 1, which is 9, right? Okay, so 6 is less than 9, that's true. When this statement is true, we change min. Min now is scan. So min, instead of being 1, it's scan, which is 2. Okay, so now it's 2. And then we increment scan. Scan now is 3, right? Instead of 2, now it is 3. Okay. And 3 is less than 5. And we come here, list sub 3 compared to list sub 2. Our main is 2. So what is that? List sub 3 is 3. Less than list sub 2, which is 6, right? Okay, which is 6. Our scan, our main is 2. Remember last round we changed it. So this is true. It's true what we do. We change main again. Main now is scan. Okay, so instead of 2, scan is 3, so main is 3. Okay, and then we increment scan. Scan now is 4, right? Okay, and 4 is less than 5. That's true. We come here, list sub scan, which is 2. Okay, the value is 2. The index is 4. So 2 is less than list sub min. Min is 3. List sub min is 3. That's the value. The index and the value happen to be the same. 2 is less than 3. That is also true. So when it's true, what we do, we change min, the index for min. And so the index for min is scan. And what is scan? Scan is 4, right? We are just mimicking the computer because the computer remembers all these values. So min is 4. And then we increment scan. Scan now is 5. And we come here, 5 is less than 5. That's not true. So we exit this loop, this inner loop. We exit. And then we do temp. Temp is equal to list sub min. List sub min is, our min is 4, right? List sub min is 2. Okay. So temp is 2. And then we do list sub min is equal to list sub index. Index is 1. List sub min is 4, right? So index is 1, that its value is 9. And so list sub min is 4. We come to this location and we place list sub index, which is list sub 1 here. Okay. Oops. Okay. So now it's 9. We are doing the swapping, right? Okay. List sub min is equal to that. And list sub index, which is list sub 1. Our index is 1 here. List sub 1 is equal to temp, which is 2. So now after 2 rounds of the outer loop, you see we have done this sublist. Okay, so I'm not going to go on, but you got the idea. So what you need to know is look at this loop. This will go through the list, okay, n minus 1 times, right? If you have n elements, then it will go through the list n-1 times. And remember, it doesn't go through the last element because it's by default the largest one. It's the leftover. And so for each of that n, for each position, remember index changes incremented by 1. So for each index of the n indices, right, it will go through this loop. And this loop, if you look at it, it's roughly the whole list n times. So for each of the n times here, it will go through the list n times. So it's basically n times n. Okay, so this is n times, right? And for each of that n times, this for loop goes n times. So the complexity of this algorithm is really n squared. And we call that the big O notation. This is how you write it. O, order, big O. Okay, so this means you have to do n squared number of comparisons in order to sort this list. So if you have 10 elements in the list, you will have to do roughly 100 comparisons to sort the list. Okay, so we went through this. Next, we will do insertion sort. Okay, now let's talk about this insertion sort. Okay, we finished selection sort, right? Selection sort, once again, I'm repeating this. It selects the smallest value element and place it in the final location, which is index 0. And you continue to do this to fill out the index. Insertion sort, okay, if you think about the name, insertion means you insert the element into the proper place. So its algorithm is to assume a sublist that is sorted, and then you have an element, you insert it into the proper place in this sorted sublist. Okay, that's the algorithm. So in more detail, you consider the first item to be a sorted sublist. So let's look at this list. We have 5 elements here. We assume this element is a sorted sublist, okay? It's sorted. And then you insert the second item into the sorted sublist. So this is a sorted list, and we look at this item and compare it with this sorted list. Is it less? If it's less, we need to insert it there. If it's greater, it stays here, right? So 9 is greater than 3, so it stays itself. It stays there. It doesn't do anything. And now these 2 elements are sorted, right? So those 2 elements are sorted. And now we look at 6, okay? We look at the next element, 6. 6 compared to 9, it's less. So we know that 9 should go after 6. So we put it here, okay? And then we compare 6 with 3. 6 is greater than 3. So 3 remains there, and 6 will go here. Okay, so after that, we have these 3 elements sorted, right? Now we look at this one, okay? We look at this one. 1 compared to the sorted list, the last element of the sorted list. So basically, when you do comparisons, you're going this way, really. Okay, when you go through the whole list, you go that way. So you compare 1 with 9. 9 is greater, so you shift 9 here. And then compare 1 with 6, it's less, so 6 needs to come here. And then you compare 1 with 3, 3 needs to come here. And that's the end. So now you place 1 here, and that is the resulted list, right? 1, 3, 6, 9. And now you have this sorted, and you have one last element, 2. So you compare 2 with every element of this list until you find the proper position. So 2 compared to the last element of 9, 9 is greater, so you need to shift it to vacate that location for 2. And 2 compared to 6, we need to shift 6 here. And 2 compared to 1, we need to shift it here. And 2 compared to, 2 compared to 3, you need to shift it here. And then 2 compared to 1, now 1 remains in its position. And now we place 2 here. Okay, and that's what this is. We place 2 here and 6 was shifted, 9 was shifted and everything was shifted. So now it's done, right? That is how this insertion sort works. And once again, if you look at it, it has 5 elements, but we only need to sort it for 4 times. It goes through the list. The algorithm really does 4 passes. When we say, once again, passes, it means it passes through each element. So we do that 4 times, 4 passes. Why? Because in this insertion sort, we assume the very first element to be sorted. Remember, in selection, we assume the last element to be sorted because it's the leftover. In insertion, we assume the first element to be sorted. That's why you need to do it 4 times instead of 5. Okay, that's the insertion sort, and this is the more detailed algorithm. Now let's trace this, and once again, I'm going to use this method just to type it out so that you understand it. Okay, so this is the method in the sorting class. Okay, it's insertion sort, and it accepts a comparable array, and we discussed that already. So once again, to trace an algorithm, you are tracing the variables, really, so you know where you are and what the program is doing, what the code is doing. So we have several variables. Index, it's 1, right? It's equal to 1. And comparable key is equal to list sub index. List sub index is 9. So that's the key. Okay. And notice that it's not 3 because remember, we are assuming the first element to be sorted. That's why we started at 1. And that's why we our key is list sub index. Okay. And int position is index. So position is 1. Okay, index is 1. And that's the outer loop. If you look at the outer loop, everybody, it's once again, it goes through each position, each index. That means it looks at each element, right? And so that you can insert it in the proper place. And we don't do the first one because the first one is assumed to be sorted. So we start from 1 to the very end. And that is to look at each element, compare it with the sorted sublist, and insert it into the proper position. And so this loop is doing the comparison, and this is doing the insertion, right? This loop is make sure we vacate the proper place. Okay, keep shifting. This is the shifting, really. So let's look at this. While position is greater than 0, that's true, right? We have 1, so that's true. And key, our key is 9, and key is greater, is less than this element. When I say that, you might be a little bit confused. Why is it less than? Because look at this code. This is saying key.compare2 this element is less than 0. Remember, if this is less than this element, current element key is less than this element, it will return a negative number, which is less than 0, right? If this element key is greater than this element, this list position -1, it will return a positive. That will be greater than. If they're equal, it returns 0. So because this is an object, you don't simply use key is less than list position minus 1. You cannot do that because they are object. You have to use the compare2 method. But the returned value, if key is less than list sub position minus 1, will be negative. That's less than 0. That's why I'm simply doing 9 is less than list sub position minus 1. Position is 0, it's 1, and that's 9. I'm sorry. Key is 9. I need to do it. I cannot do it this way. This will confuse myself. So 9, that's the key, right? Key compared to list sub position minus 1. Position is 1. 1 minus 1 is 0. So the element at 0 is 3. Okay. 9 is less than 3. That's false, not true. So we bypass the body. Okay. And then we come here, right? We come here. The body is bypassed for this loop. And we come here, list subposition, that's this location. It's equal to key, which is 9. So it's swapping with itself. You still have to do this because this is the code in the algorithm. The computer will just blindly assign itself to itself. So now we have these two sorted. This is a sorted sublist. So this code, the for loop first round is done. We increment index. Index now is 2. Okay, I will just delete that, right? Index now is 2. And 2 is less than list sub length, 5, that's true. Comparable key is equal to list sub 2. So key now is list sub 2, which is 6, right? Okay, which is 6. That's this one here, 6. Okay, and int position is equal to index. Position is equal to index. So now position is 2. And so now we are, instead of doing that, we are doing what? We go to this while loop. While position is greater than 0, that's true. Q is greater than 0, and key is 6. 6 is less than list sub position minus 1. That is list sub 1, right? 2 minus 1. List sub 1 is 9. 6 is less than 9. That's true. Okay, that's true. And we do what? We come into the loop body. We do list position is equal to list position minus 1. That is list sub 2. That's the position, right? List sub 2 is equal to list sub 1. That means this is 9. Okay, that's what it is right now, right? Okay, and after that, we do position minus 1. So position now, instead of 2, it becomes 1. Okay, and then we do position minus 1. Then we go back to the while loop condition. Position is greater than 0. That's true. Key is compared to list sub position minus 1. So key is 6. Is it less than list sub position minus 1 is 0? Is it less than list sub 0, which is 3? Okay. Is it less than 3? Right? 3. 6 is less than 3? No, that's not true. It's not true. So we get out of the loop. We come here. We execute this statement, which is list sub position, which is list sub 1, is equal to key. Our key is 6. So now it's 6. Okay, so we have this sublist now, right? And then we go back to the for loop. We increment index, right? So index now is 3, okay? And we come here, comparable key is list sub 3, which is 1, which is this one, right? Which is 1, that's our key. And then in position is index. So position is 3. It's the same as index. Okay, And then we come to this while loop. Position is greater than 0. That's true. And key dot compared, our key is 1, compared to list sub position minus 1. Position minus 1 is 3 minus 1. That's list sub 2. List sub 2 is 9. It's 1 less than 9. That's true, right? That's true. So we come into this loop body and we do list sub position is 3. List sub 3 is equal to list sub 2. Position minus 1 is 2. So list sub 3 is list sub 2, okay, which is 9, right? Okay. And then position minus minus. Position now, instead of 3, it's 2. Okay. And we go back to the while loop. Position is greater than 0. That's true. Key, which is 1, is less than list sub position minus 1. Position is 2, minus 1 is 1. So it's less than list sub 1. List sub 1 is 6. Okay, 6. And that is true, right? It is true. So we come into the loop body, list sub position, which is this location, position is 2. List sub position is equal to list sub position minus 1. That is list sub position 1. Okay, so we are shifting. If you look at it, right, this is what we are doing. We are shifting the value, the larger value, to the right. Okay, and position minus minus. Position becomes 1. Okay, we go back to the loop. Position is still greater than 0, and key is what? Our key is still 1, right? Key is less than list sub position minus 1. Position is 1. 1 minus 1 is 0. List sub 0 is 3. Okay, so 1 is less than 3. That is true. And so what do? We come in, list sub position, which is 1. List sub position is equal to list sub position minus 1. That is list sub position 0. So it's 3, right? And position minus minus. Position now becomes 0. And we go back to the loop. Position is greater than 0. This condition is false. So we get out of the loop and we come here. List sub position is equal to key. So list sub position is 0. It's equal to key. Key is 1. So list sub position is 1. Okay, now we have the, we will just finish this, right? You can see this is much easier to trace, actually. So these are sorted. Now we go to the 4th round. So we increment index. Index now is 4. And 4 is less than 5. That's true. Comparable key is equal to list sub index, which is 2, right? Which is this value, sub 4. Okay, while position is greater than 0, we need to do this. Position is index, so our position is 4. Okay, so while position is greater than 0 and key, I am going to, okay, I can just go to the next line. And our key instead of, is it 2? Yes. Okay, so 2 is less than list sub position minus 1. Position minus 1 is 3. That's this one, right? So 2 is less than 9. That's true. And when it's true, what do? We do list sub position. We do the shifting. List sub position is equal to the previous element. So list sub position is this position. It's equal to list sub position minus 1, which is 4 minus 1 is 3, which is 9. So now we put 9 there. Okay, we are shifting. You see the shifting of this element to the larger index. Okay, and then position minus minus. So position now is 3. And we go back, greater than 0. Key is what? Key is 2, right? 2 is less than list sub position minus 1. Position is 3, position minus 1 is 2. So 2 is less than 6. That is true. And we come in list sub position, which is 3. Position is 3, right? List sub position is equal to list sub position minus 1. So position minus 1 is 2. So this location is equal to position sub 2, list sub 2, which is what, 6. Okay. And then position minus minus, position now it's 2. And let me put a comma there. It's 2. And we come here, greater than 0, and key dot compared to list sub position minus 1. Position is 2. 2 minus 1 is 1. So we are looking at this element, 3. So 2 is less than 3. That's true. So we go into the loop body, list sub position. Position is 2. That means this location, right? This location should store the value of list sub position minus 1. That is list sub 2 minus 1, which is 1. The element is 3, so we should place 3 there. Okay, and position minus minus. So now position becomes 1. Position is greater, go back to the loop header, and position is greater than 0, that's true. And the key, which is 2, let's see, 2 is less than list sub position minus 1. Position is 1, 1 minus 1 is 0. The element at that location is 1. So 2 is less than 1. That's not true. We get out of the while loop finally, and we come here, right? We come here, and then let's supposition our position is 1. Okay, it's equal to key. Key is 2, so this location should be 2. Okay, now we increment index. Index now is 5, right? 5. Oops, cannot type. 5 is less than 5. That condition is not true. We get out, and so the list is sorted. That's how this algorithm works, everybody. Okay. And for this one, this goes through each element, each position, and this will compare that element with everyone in the sublist. So it is really an n times n situation again. So the, what do you call that? The complexity is once again n. Oh, that's n, and this is n also, multiply, right? For each index, you will do it this many times. Okay, that's n times. For each index, you do n times. So there are n indexes. So it's n times n, which is n squared. That is the big O. We call that big O. Okay, order, big O notation. This tells you the complexity. That means you have to do n squared number of comparisons to sort the list. Okay. And this is a tracing, which I did just now. This is just a different set of data. And an example, another example for selection sort, another example of insertion sort. You can look at it. Comparing sorts, okay? Let's talk about this. Both of them are of O n squared, okay? But if you think about it, insertion sort is a little bit more efficient because once the element is not less than the last element of the sorted sublist, it doesn't do any comparisons. So that's why it is a little bit more efficient, but on the grand scale, okay, they are the same because you need a nested loop. When you have a nested loop, it's always n squared, okay? So you can read this. I explained that already. You can read that. And this is what we call the big O notation, okay? The big O simply means order. And there are other sort algorithms which are more efficient, n log n, but we are not talking about them. We talk about them in class 3. Okay, so you need to remember this, everybody, the complexity. So just to let you know, when you have a test, what I ask you will be something like this. After the second round of the selection sort or insertion sort, what is the value? What does the list look like? So you have to give me this list correctly. That's what I'm going to ask you. Let's look at the last item, searching. Okay, searching is pretty easy to understand. That means you are trying to find an element in the list, right? The search pool, the number of elements is always called n, okay? So when you search, you have a target, you want to find it in the list. And once again, we define the method using the comparable parameter, okay? And so we will look at a simple search, simple classic search algorithm, which is linear search. Originally, I do have the binary search, but given the nature of this semester, I deleted that part. So we will only go through linear search, and binary search will be discussed in class 3 anyway. It's the most famous searching algorithm and the most efficient searching algorithm. But we will not discuss that here. So let's look at this search. Linear search, very intuitive. Okay, you begin at the one end of a list and examines each element and compares it with the target element in turn. This requires repetitively comparing the target to candidates in the search pool. Eventually, either the item is found or the end is encountered. So if you have a target here, you compare that with this element. No, not it. No, no. You see, you're comparing it with each element. So if you have n elements and you're looking for an element, a target, what is the big O? What's the order of complexity? Think about it. You're comparing it with each one of them. It will be O(n), right? You have to go through every element. That's the worst case scenario. If your element, the target is the last one, you have to go through every element. If the target is not in it, you have to go worst case scenario. The best case would be it's right here, the very first element, the one comparison you found it. The average case is, of course, n divided by 2, right? But n divided by 2, we discard the constant, is still n. That's why we call it O(n). Okay, for linear search, the algorithm is O(n). The complexity is O(n). So here is an example, a list of numbers. Suppose we're searching for number 9. We compare 9 with 4, not true. Then we continue, increment our index to 1 and compare it with this. No, no, no. Oh, found it. So we stop, right? And this one, if we are looking for 0, compare, no, compare, no, compare, no, compare, no, compare, no. We exhausted the list, so we get out. And we know that we did not find it. Okay, let's look at this. Okay, let me, this is pretty easy to understand, but I'm going to stop it first. I really feel this is a little bit unnecessary maybe, but hopefully this helps you understand it much, much better, okay? Because this algorithm is so straightforward. That's why I feel a little bit unnecessary. But if you look at it, it returns a comparable, okay? That's important to know. That means it returns the element, okay? And that's the class name, that's the name. And notice all of them are static, right? This insertion sort, selection sort, they are all static so that you don't have to create an object. You just use sorting dot linear search. And it accepts 2 parameters. One is the list itself you want to search in, and one is the target you are searching. Okay, so our index is first 0. Suppose we want to find 6. Okay, so our index is 0 and found is false. Oops, right? Found is false. Okay, and so not found, that's true. Not false, right? Not false, that's true. And the index is what? Index is 0, less than list sub length, that's less than 5, that's true. And if list sub index, which is this one, if list sub index dot equals target, we are not using we are not using this because once again, this is comparable. It's an object. It's not primitive data type. So we use the equals method, okay? So if it equals to target, if we are looking for 6, list sub index is this one, not equal to 6. So found, we go to else, index plus plus. So index now is 1, right? And then we look at this one, list sub index, list sub 1 compared to 6, are they equal? No. And we increment index 2. And not found is still true, less than 5 is still true. List sub 2 is equal to the target? Yes, right? Yes, that's true. So we this condition is true, and we change found to true. So found now is true. Okay, and not true, that's false. This will give you false. So you get out of the while loop and you simply return the element. Okay, suppose we are looking for 0. Let's continue. Okay, so 6 and 0 now the same. We increment index to 3. Okay, list sub 3 is equal to 0. No, we increment index to 4, right? List sub 9 is equal to 0. No, we increment index to 5. Okay, to 5. And let's see, found, just now it was false, right? We are looking for 0. So not found, not false is true. So this condition is true. But index, when it's 5, it's less than list sub dot length, list dot length, which is 5. 5 is less than 5. That's not true. So we get out of the while loop. And found is still false. So we return null. Null means it doesn't exist. It doesn't point to anything. So then we get out. That's the linear search. If you look at this, we are going through each element. So this is a one layer loop. It's not nested. So it is, what do you call it? It is a linear. That's why we call it linear. And the complexity is O n. Okay, and that's how you look at it. Okay, everybody, that's it.